In this video, we're going to focus on solving problems associated with Hess's law. Now, let's say if we have a reaction, A plus B turns into C. And let's say the enthalpy change for this reaction is 100 joules. And we're going to have another reaction, C plus D turns into E. And the enthalpy change for this reaction is 200 joules. Now let's add these two reactions. If we add them, C will cancel because we have one on the right and one on the left. Everything else will simply fall down to the third equation. So A and B is on the left and D is on the left. So they're going to remain on the left side. To the right of the arrow, all we have left over after we cancel C is E. Now, according to Hess's law, since we add equations 1 and 2 to get equation 3, the enthalpy change of equation 3 is the sum of the enthalpy changes for equations 1 and 2. So it's going to be 100 plus 200, which is 300. And that's the main idea behind Hess's law. You want to use the enthalpy values of other reactions to predict the enthalpy change for a different reaction. Now, there's something else that you need to know. There are some rules that we need to go over. So let's consider this reaction again. Now, if we multiply the reaction by 2, let's say if it's 2A plus 2B yields 2C, what effect will it have on the enthalpy change for that reaction? If you multiply the reaction by 2, you need to multiply the enthalpy change by 2. So it's going to be 200 joules. Likewise, if you multiply by a half, you must also multiply the enthalpy change by a half as well. So half of 100 is 50 joules. And if you reverse the reaction, the sign of the enthalpy change will change. So right now, it's positive 100, but now it's going to be negative 100. So here's a practice problem for you. Let's say if you have this reaction, 2A plus 2B yields 2C. And let's say the enthalpy change is 300 joules. And you also have E yields C plus D. And let's say the enthalpy change for that is negative 400 joules. So using those two reactions, calculate the enthalpy change for this reaction. A plus B plus D turns into E. What is delta H for this reaction? So how can we use equations 1 and 2 to calculate the enthalpy change for equation 3? So we need to adjust equations 1 and 2 in such a way that when we add them, it's going to give us equation 3. And therefore, the enthalpy change for that reaction will simply be the sum of these values. Of course, after we modify those values. So, how should we begin? Now, you want to focus on a letter that is only found in equations 1 or equation 2, but not both 1 and 2. So let's focus on A. Notice that in equation 1, we have 2A, but there's no A in equation 2. So if we look at equation 3, we need 1A, not 2A. So therefore, that tells us that we should multiply equation 1 by a half. Now, equation 2, let's focus on E. E is only found in equation 2, but is not found in equation 1. I wouldn't focus on C because it's found in both 1 and 2. For reactants and products that are found in multiple reactions, you want to avoid focusing on those substances because it can be confusing dealing with those. It's easy to focus on E because E is only found in equation 2. So notice that we need to reverse equation 2 so that E could be on the right side. So let's reverse it. So equation 1 will now be A plus B turns into C, and then we need to multiply 300 by half. 300 divided by 2 is 150. Now equation 2, we're going to reverse it. It's going to be C plus D turns into E. And since we reverse it, this is no longer going to be negative 400. It's going to be positive 400. So now, let's add the two reactions. If we add them, notice that C cancels. And it's going to be A plus B plus D turns into E. So now all we need to do is add these two values. So 400 plus 150 is 550. So that's going to be the enthalpy change for the new reaction according to Hess's law. Let's try another example. Water decomposes into hydrogen gas and oxygen gas. And the enthalpy change associated with this reaction is going to be positive 572. Hydrofluoric acid, HF, decomposes into hydrogen gas and fluorine gas. And the enthalpy change for this reaction is going to be positive 542. So let's use these two equations to find the enthalpy change for the following reaction. Fluorine reacts with water to produce hydrofluoric acid and oxygen gas. So let's call this reaction 1 and reaction 2. So how can we modify reactions 1 and 2 such that it's going to add to the net reaction that we want? Feel free to pause the video and work on this example. Now you want to focus on the right substances. So we don't want to focus on hydrogen gas because it's found in equation 1 and 2. Let's focus on water. Notice that water is already in the appropriate side of the reaction, which is on the left side. And we have the right number of water molecules, which is 2. So we don't need to change equation 1. So let's rewrite it. So everything is going to be the same, and the enthalpy change will remain positive 572. Now what about equation 2? What modifications do we need to make to it? So let's focus on HF. In equation 2, we have 2 HF on the left side, but we want 4 HF molecules on the right side. So not only do we need to reverse equation 2, but we must also multiply it by 2. So once we reverse it, H2 and F2 will now be on the left side. And if we multiply by 2, we're going to have 2 H2 molecules and 2 F2 molecules on the left side. On the right side, we're only going to have 4 HF molecules. Now, the positive 542 is going to be negative, and we need to multiply 542 by 2, which is going to be 1084. So now let's add the reactions to make sure that it adds up to the net reaction that we want. So the first thing you want to do is identify what cancels. Hydrogen gas cancels. Now we have water and F2 on the left side. So that's going to be in the left side of the net reaction. And on the right side, we have O2 and HF. So notice that this is the same as the reaction that we want. So what that means is that we can now add the enthalpy values to get the enthalpy change for the whole reaction. So negative 1084 plus 572 is negative 512. So this is the answer. Let's try another example. Ammonia decomposes into nitrogen gas and hydrogen gas. And let's say the enthalpy value for this reaction is positive 92. Water is going to decompose into hydrogen gas and oxygen gas. And just like last time, the enthalpy change is positive 572. But now we're going to have a third reaction. Nitrogen plus oxygen reacts to produce nitrogen monoxide. And the enthalpy is going to be negative 180. So using these three reactions, calculate the enthalpy change for this reaction. Ammonia plus oxygen gas produces nitrogen monoxide and water. So let's start with the first reaction. How should we change it? What should we do? So let's identify the substances that we shouldn't focus on. Don't focus on N2 because it's found in reactions 1 and 3. Don't focus on H2 because it's found in the first two reactions. And don't focus on O2 because it's found in multiple reactions in equation 2 and 3. So for the first equation, we're going to focus on NH3 because it's only found in equation 1 and not in reaction 2 and 3. So notice that we need to double equation 1. NH3 is already on the appropriate side, but we have 2 and we need to get to 4. So let's multiply the first reaction by 2. So it's going to be 4 NH3, and that's going to turn into 2N2 plus 6H2. Now we need to double the enthalpy change. 92 times 2 is positive 184. Now what about the second reaction? Do we need to change it? So let's focus on water since it's only found in reaction 2 but not in reactions 1 and 3. So we need 6 water molecules on the right side. We have 2 on the left. So we need to reverse it and multiply it by 3. So I'm going to write 3R times 3 and R for reverse. So H2 and O2 will now be on the left side. So 2H2 times 3, that's going to be 6H2. And then O2 times 3, that's 3O2 on the left side. And on the right side, we're going to have 6 H2Os. So now the positive 572 will now be a negative number. And 572 times 3 is negative 1716. So now let's look at the last reaction. The only thing that we should focus on in reaction 3 is NO. It's only found in reaction 3, but not in 1 and 2. We need 4 NO on the right, but we only have 2 on the right, so we don't need to reverse it, but we do need to multiply by 2. So it's going to be 2N2 plus 2O2 on the left, and 4 NO on the right. So we need to multiply negative 180 by 2, so it's going to be negative 360. Alright, so let's make some space. Now let's add the 3 reactions. So let's identify the things that cancel. So nitrogen gas cancels, hydrogen gas cancels, and that's about it. So on the left side we have 4 NH3 and we can add 3 plus 2 oxygen molecules. So that's going to give us a total of 5 oxygen molecules. And then we have 4 NO on the right side and 6 H2O molecules. So at this point, what we need to do is add these 3 values. So it's going to be 184 minus 1716 minus 360. So the enthalpy change for the whole reaction is equal to negative 1892. So this is the answer. For the sake of practice, let's try one more example. So just like before, water decomposes into hydrogen gas and oxygen gas. And the enthalpy is going to be 572. Carbon dioxide decomposes into carbon plus oxygen. And this is going to be positive 394. And then acetylene reacts with oxygen gas, and that produces carbon dioxide and water. And the enthalpy change is going to be negative 2600. So using these 3 reactions, calculate the enthalpy change for this reaction. Acetylene decomposes into elemental carbon and hydrogen gas. So which species or substances should we not focus on? Don't focus on O2. It's found in multiple reactions. Don't focus on CO2. And let's not focus on water. So in the first reaction, we should focus on H2. It's only found in reaction 1. So it's already in the appropriate side, but we need to divide the first reaction by 2 because we only need 1 hydrogen molecule, not 2. So let's multiply the first equation by 1/2. So it's going to be H2O, which turns into H2 and 1/2 O2. So half of 572, or 572 divided by 2, that's going to be positive 286. Now let's move on to the second reaction. Let's focus on carbon. It's only found in equation 2. So we need 2 carbons on the right. So therefore we need to multiply equation 2 by 2. So it's going to be 2CO2. We don't have to reverse it. And this is going to turn into 2 carbon atoms and 2 oxygen molecules. So 394 times 2 is positive 788. Now what about the last reaction? We need to focus on acetylene. It's only found in reaction 3, but we only need 1 of them. So we got to multiply the reaction by 1/2, but we don't have to reverse it. So half of 2 is 1, so it's just going to be C2H2. Half of 5 is 5 over 2, which is equal to 2.5. Half of 4 is 2. Half of 2 is 1. And half of 2600 is 1300. So now let's add these 3 reactions. So first, let's see what we can cancel. We can cancel water, and we can cancel CO2, and we can cancel the oxygens. On the left side, we have 2.5 oxygen molecules. On the right side, we have 2 plus 0.5, which is 2.5. so they cancel each other. So on the left we have acetylene, C2H2, and on the right we have 2 carbon atoms and H2 gas, which equals what we have here. So now we can add these 3 numbers. So 286 plus 788 plus negative 1300 will give you negative 226. So that's the answer.